Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up Chapter 7 by taking a look at Section 7.2. This will be sort of our last section, sort of discussing different linear algebra concepts, and then from here on, we'll be moving into Chapters 8 and 9, returning to our study of differential equations. So let's go ahead and take a look at this. Some of the concepts that we are going to be talking about in this video, we've already discussed from the previous ones where we were learning about eigenvalues and eigenvectors. So let's start with the definition here. We're going to let A be a square matrix that's n by n, and we're going to let lambda be some eigenvalue of A. Then the eigenspace of that eigenvalue is a subspace of Rn, if the eigenvalue is real, or Cn, if the eigenvalue is complex, defined by all the solutions V to A minus lambda In times V equals 0. So remember that this is basically saying that the eigenspace is the subspace that consists of all the eigenvectors for a given eigenvalue. Now, when we talk about eigenspaces, we often write them as E sub lambda. So whatever the value of lambda is, we would say E sub that value for the eigenspace. Now, technically, if we were being really formal, we should probably try to prove that the eigenspace is truly a subspace. But in some ways, we've already done that because of our discussions of solution spaces to homogeneous systems of equations. This equation here is a homogeneous system of equations. So by its very nature, the solution space must be a subspace. So we've already done that work, so we're not going to repeat that proof. We know that eigenspaces really are not just subsets, but they are subspaces. A sort of important theorem that ties together some of the concepts we introduced in the previous video and some of the things we've discussed whenever talking about subspaces is the following. So we're going to let lambda be an eigenvalue of A with multiplicity m sub lambda. So we have some eigenvalue and we have its multiplicity. Remember, the multiplicity is simply how many times that root appears as a solution to the corresponding characteristic polynomial. In other words, it's basically how many times that root is repeated as a solution to the corresponding polynomial equation. So this theorem then says that the dimension of the corresponding eigenspace is less than or equal to that multiplicity. In other words, the dimension is always limited by the multiplicity. So you will never have the dimension of the eigenspace be greater than the multiplicity, though you may have it less than that multiplicity. Now, this theorem is actually a pretty complex one to prove. It actually, if you look in your textbook, they just quote another textbook that's a little bit more advanced that runs through a proof of that. So we're not going to actually go ahead and prove this theorem, but what I would like to say is if you go back on all of the examples that we've done so far when we were generating those eigenvectors, we didn't call them eigenspaces yet, but we did give the general form for the eigenvector, and we often saw how many free parameters it would have. If you go back and you check, you can see that in every previous example, the number of free parameters, which corresponds to the dimension, was always less than or equal to the multiplicity of every eigenvalue. So that's certainly not a proof, but it is a justification that this is always going to be the case. We will see one more example of calculating some eigenvalues, eigenvectors, and eigenspaces. And again, we will confirm that this dimension is always less than or equal to the multiplicity. All right. Now we have a theorem that we are going to go ahead and prove because it is a pretty interesting and very important one. So for this theorem, we're going to say that eigenvectors corresponding to distinct eigenvalues are linearly independent. Now, this is a really interesting theorem. What this is basically saying is if you have an eigenvector for one eigenvalue and you take an eigenvector for a different eigenvalue, it is guaranteed that those two eigenvectors are going to be linearly independent. And to prove this, we're actually going to do a proof by induction. So I think it's worthwhile to actually go through that. So to start off with, we're going to let A be n by n with distinct eigenvalues, lambda 1, lambda 2, down to lambda m. Again, we don't know how many eigenvalues there are, but I mean, certainly this m has to be capped less than or equal to that n because, of course, we know that the eigenvalues are roots of the characteristic polynomial, and the characteristic polynomial is going to be of degree n, so it can have at most m roots, or at most n roots. So we know that m is less than n, but that's not really relevant for this proof. So we're just going to say that these are distinct eigenvalues, lambda 1, lambda 2, down through lambda n. Now, of course, what distinct eigenvalues mean is that none of these are equal to one another, right? So we're saying if any of them are repeated, throw those out and just look at a list where there are no repeats. So as sort of a note here, we can sort of note that lambda 1 is not equal to lambda 2, which is not equal to lambda, we don't need to say lambda 3, we'll just go down, dot, 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 not equal to lambda m. Okay? And let's let v sub I be a eigenvector for lambda I. So we're going to let our notation be v sub I is an eigenvector for the corresponding eigenvalue. So what we need to show is we need to show that v1, v2, down to vm is linearly independent. All right, so to do this, what we're going to do is we're going to do a proof by induction based on how many eigenvectors we actually have. So we're going to do this as a proof by induction. So we're going to first consider as our base case that we only have one. So we only have one eigenvalue and one eigenvector. Well, obviously then, if we have our eigenvector, since our set then will just be v1, this is obviously linearly independent, right? The only way that a single vector could be linearly dependent is if that vector was the zero vector. But remember, when we're talking about eigenvectors, right? Well, then we know that we're assuming that that's going to be, that they were going to talk about those non-zero solutions. So v1, obviously by itself, is going to be linearly independent. So that's our base case. So now we're going to assume this is Li for m equals k. So we're going to say that if we go v1 through vk, it's guaranteed to be linearly independent. And what we need to show is it is linearly independent for m equals k plus 1. So if we go one further, if we have k plus 1, then it'll still remain linearly independent. So we need to show that this v1, v2, down to vk, comma vk plus 1 is linearly independent. Okay? If you think about how you show things are linearly independent, well, we think about this equation, c1v1 plus c2v2 plus dot 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 ckvk plus ck plus 1 vk plus 1 equals 0. And now we can say that our need to show is that C1 equals C2 equals CK equals CK plus 1 equals 0. Because remember, the definition of being linearly independent is that the only way you can do a linear combination and get the zero vector is if all the constants or coefficients are uniformly 0. All right, so let's think about this real quick. We're going to do one quick thing with this. What I want to do here is I just want to rearrange it in terms of this new vector. So from here, I'm just going to view this as ck plus 1, vk plus 1 is equal to negative c1v1 minus c2v2 minus dot 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 minus ckvk. Now, I'm not going to go any further than that, and specifically, I'm not going to divide by ck plus 1, because then I would need to assume that ck plus 1 is not equal to 0, and my goal is actually to show that ck plus 1 is 0, so I'm definitely not going to go any further than this. So I'm just going to note this sort of rearrangement, and we'll need this in just a moment, so we'll just save this here. Okay, so we've got that. Now, let's go back with this and do something a little bit more with it. So now, let's also take this guy and just continue on with it in this form. Okay, now, interestingly enough, right, so far we haven't really brought in the eigenvalue-eigenvector relation. So we know that these v1, v2, vk, vk plus 1 are all eigenvectors. So let's multiply by that matrix A because we know a relationship there. So let's go ahead and multiply on both sides by A. So we would get C1 AV1 plus C2 AV2 plus CK AVK plus CK plus 1 AVK plus 1 equals, and then of course any matrix times the 0 vector is going to be that 0 vector there. We can all go ahead and write that out just so we can see that we're doing it on both sides, A times 0. Okay, now let's go ahead and remember that each of these guys is an eigenvector. So when we do our matrix multiplication, that's equivalent to scalar multiplication by the corresponding eigenvalue. So this becomes C1 lambda 1 V1 plus C2 lambda 2 V2 plus CK lambda K VK plus CK plus 1 lambda K plus 1 VK plus 1. And of course, this is going to be the 0 vector over there. Okay, but we know one thing further. We also came up with this nice relation in terms of VK plus 1. We said it's equivalent to that. So let's go ahead and sub that in, and we're going to sub that in for CK plus 1 times VK plus 1. So we're basically going to imagine this guy's out in front and distribute it onto all that. So doing that, we would get C1 lambda 1 V1 plus C2 lambda 2 V2 plus CK lambda K VK plus lambda K plus 1 times that whole expression, which is minus C1 V1 minus C2 V2 minus minus CK VK is all equal to 0. All right. Now, let's gather the like terms. Let's gather everything that's got a V1, everything that's got a V2, etc. So in terms of the V1 stuff, you'd get C1 lambda 1, and then you get minus C1 lambda K plus 1. So we get C1 lambda 1 minus C1 lambda K plus 1 times V1 plus C2 lambda 2. You get that on V2, and then minus C2 times lambda K plus 1. So minus C2 lambda K plus 1 V2 plus plus last one CK lambda K minus CK lambda K plus 1. So plus CK lambda K minus CK lambda K plus 1 VK equals 0. Okay. But now, remember that V1, V2 through VK, by assumption, is, well, we said we're going to assume that they are linearly independent when m equals k. So in other words, we're assuming they are linearly independent when you have V1, V2 through VK. So since this equation is equal to 0, that means each of these constants must be equal to 0 by the definition of linearly independent. So since V1, V2 through VK is linearly independent, that tells us that C1 lambda 1 minus C1 lambda K plus 1 equals 0. C2 lambda 2 minus C2 lambda K plus 1 equals 0. All the way down to CK lambda K minus CK lambda K plus 1 equals 0. But let's do a little clever factorization. C1 lambda 1 minus lambda K plus 1 equals 0. C2 lambda 2 minus lambda K plus 1 equals 0. All the way down, our last equation would be CK lambda K minus lambda K plus 1 equals 0. Now, what's interesting about this is that in each of these products, right, it's multiplying together to be 0, which means that one of these things, either C1 or this difference has to be 0, C2 or this difference has to be 0, CK or this difference has to be 0. But remember, these guys, lambda 1 minus lambda K plus 1, lambda 2 minus lambda K plus 1, lambda K minus lambda K plus 1, cannot be 0. These can't be 0 because we assumed all the lambdas, all the eigenvalues, are distinct values, meaning they can't be the same, so these guys cannot be equal to 0. So lambda 1 minus lambda K plus 1 not equal to 0, which means C1 must be 0. If you have a product of two things, if one of them can't be 0, then the other must be 0, if you're having it equal 0 as a product. Lambda 2 minus lambda k plus 1 can't equal 0, so that means C2 is 0. And all the way down, for this guy, this would tell us that lambda k minus lambda k plus 1 not equal to 0, so ck equals 0. So we've shown that C1, C2, all the way down to ck must be equal to 0. Now, if we go back and think about that, that's almost what we needed to prove. We needed to prove, if we look back here, that C1 through ck plus 1 are all 0. And we've just done that all of these are equal to 0. So we still need to show why ck plus 1 is equal to 0. But let's think about that. If we actually look at our equation right here, right, we've just found out that all of these are equal to 0. So if this is going to be equal to 0, well, we know that vk plus 1 is not 0 because we don't look at zeros as eigenvectors. So that means that ck plus 1 must also be 0. So finally, since vk plus 1 is not equal to 0, this implies that ck plus 1 equals 0. So C1 equals C2 equals ck equals ck plus 1 equals 0, which implies that it is linearly independent. Now, I know that this is a pretty messy proof overall. I wanted to do it because, to be honest, this is sort of our last chance to do an example of a proof that involves linear independence and some of the things that we've been talking about in linear algebra, and I think it's worthwhile to see that. It's also nice to see a proof by induction sort of used in one of our actual theorem, or sort of our class theorems, rather than just sort of as a random problem. So I think there's some definite things for making sure you read through this proof and understand the main ideas of it. But what you should really, really take away from this is what this theorem is saying, because it has a very simple statement. It's just saying that if you grab eigenvectors from distinct eigenvalues, those are guaranteed to be linearly independent. And if you think about that, what that basically means is if you take a basis for the eigenspaces, then when you combine all the linearly independent eigenvectors for one eigenvalue with all the linearly independent eigenvectors from a different eigenvalue, that set still will be linearly independent. So if you have enough eigenvectors from all your different eigenspaces and it matches your dimension, then it's guaranteed to be a basis. So we're going to make a couple follow-up comments to this and then get to our example. So, as a sort of final definition here, let's let A be an n by n matrix. And we're going to assume that if A has n linearly independent eigenvectors, then A is said to be non-defective. And we actually briefly mentioned this terminology in our last video. So if the number of linearly independent eigenvectors matches the size of the matrix, then we call that matrix non-defective. If you have less than n linearly independent eigenvectors, then A is said to be defective. So we've got 3 quick follow-ups to this. First, by the previous theorem, if A is non-defective, you can form a basis for Rn or Cn using the eigenvectors of A. Because we know if you take all the different eigenvectors, they'll remain linearly independent from each separate eigenspace. If you put them all together and you're non-defective, meaning you have n of them, then that'll match the dimension of Rn or Cn, so you will be able to form a basis. When you form a basis out of eigenvectors for a particular matrix, we call that an eigenbasis. If A has n distinct eigenvalues, then A is automatically non-defective. We know that every eigenvalue automatically has at least one eigenvector. We just showed that each eigenvector from a different eigenvalue is linearly independent. So if you have n distinct eigenvalues, well, then you're automatically going to be non-defective because each eigenvalue is going to give one independent eigenvector, and then you're guaranteed to be non-defective. Finally, we're going to relate the concepts of sort of the dimension and the multiplicity. A is non-defective if and only if, for all eigenvalues lambda, the dimension of the eigenspace matches the multiplicity. Now, this theorem, your book briefly gives a proof, but basically the gist of that proof, because I don't think it's really worth necessarily going through the whole thing, You can certainly read it for your own sort of benefit, but the idea here is that if one of the eigenspaces is missing an eigenvector or several eigenvectors, the other eigenspaces can't make up for that. And that's simply because we know the dimension of the eigenspace is capped by the multiplicity. So since they can't go beyond their multiplicity, if one of them is lacking, there's no way to make that up amongst the others. So the only way you're going to be non-defective is if for every eigenvalue, the dimension of the eigenspace, or the number of linearly independent eigenvectors for that eigenvalue, exactly matches the multiplicity. You'll notice also that follow-up 2 is a special case of this, because if A has n distinct eigenvalues, then every multiplicity is going to be 1, and this is going to be trivially true, so you know that if you have n distinct eigenvalues, you're automatically non-defective. All right, let's put all of this terminology together into one example here. All right, so we've got this massive matrix that we're going to be looking at here. This is a 6x6 matrix here, so we've got a 6x6 square matrix. We're going to determine all the eigenvalues, all the eigenvectors, all the eigenspaces. We're going to state the dimension of each eigenspace, and then we're going to determine if this matrix A is defective or non-defective. Now, this could be a tremendous amount of work. Nobody wants to expand a 6x6 determinant and also deal with finding out the roots of a 6th-degree polynomial. But as you guys will see, this is very nice and easy because already you can see that it's going to be upper triangular, so things should go pretty quickly here. So as always, let's start with the eigenvalues. So let's go ahead and take the determinant of 2 minus lambda, 0, 1, 0, 0, 2, 0 minus lambda, 0, 1, 1, 0, 0, 0 minus lambda, 1, 0, 2, 0, 0, 0, 1 minus lambda, 1, 0, 0, 0, 0, 0, 1 minus lambda, 1, and then 0, 0, 0, 0, 0, 1. Okay, 1 minus lambda, because we're taking lambda off the diagonal. So you can see our diagonal elements 2, 0, 0, 1, 1, 1, all received a minus lambda there. And of course, we're going to be setting that determinant equal to 0. And like we said, since it is upper triangular, we're just going to take the we want our nice laser pointer there, right? We want the product of those diagonal elements. So we have 2 minus lambda, minus lambda, minus lambda, 1 minus lambda, 1 minus lambda, 1 minus lambda equaling 0. So what eigenvalues do we get? Well, from this first guy, we get lambda equals 2. That'll be an eigenvalue. The multiplicity for that guy would be m equals 1. It only shows up once. From these guys, we would get the same eigenvalue twice. It would be lambda equals 0, which would be multiplicity 2. And then from these three, we get lambda equals 1, and that eigenvalue would be multiplicity 3. So before we get too far into the computations, I want to just make a couple mentions to make sure you guys understand the consequences of the previous theorems we talked about. For this guy here, we already know that when we go to look at his eigenvectors, his eigenspace, that the eigenvectors will have one free parameter and the dimension of the eigenspace will be equal to 1. And that is because the multiplicity is 1. When we go to look at this guy, we will find that the eigenspace is either dimension 1 or dimension 2 because the multiplicity is 2. So when we look at the eigenvectors, there will either be one free parameter or two free parameters. If we find that the dimension of the eigenspace here is equal to 1, then we will automatically know that A is going to be defective because one of the dimensions does not match the multiplicity. If we find that the dimension of the eigenspace for eigenvalue 0 is equal to 2, then we won't know yet if it's defective or non-defective because we'll have to examine this guy. When we go to do this one and we look at the eigenvectors are either going to have 1, 2, or 3 free parameters. In other words, the dimension of the eigenspace for lambda equals 1 is either going to be dimension 1, dimension 2, or dimension 3 because the multiplicity is equal to 3. If this guy has dimension 2 and this guy has dimension 3, then matrix A will be non-defective. And if we take an eigenvalue from here, 2 separate eigenvalues from here, and 3 separate eigenvalues from here, we'd be able to create an eigenbasis for the R6. So let's go ahead and go into our computations here. So let's go ahead and start with lambda equals 2. So eigenvectors slash eigenspace for lambda equals 2. So we want to subtract 2 off those diagonal elements and then augment with the 0 vector. So we'll have 0, 1, 0, 0, 1, 0, 0, 2, and then augment with 0. Then we'll have 0, negative 2, 0, 1, 1, 0, and 0. And then we'll have 0, 0, negative 2, 1, 0, 2, and 0. And then we'll have 0, 0, 0, negative 1, 1, 0, 0. Looks like we'll need a little bit more room. So let's just move that stuff down a little bit. Okay. For row 5, we'll have 0, 0, 0, 0, minus 1, 1, 0. And then finally 0, 0, 0, 0, minus 1, 0. So as you can see there, we will avoid parameterizing all of these guys. And so we will let x1 be equal to our 1 free parameter t. As predicted, we knew that since this guy was multiplicity 1, the eigenspace was only going to have 1 dimension, so there's only going to be 1 free parameter. If we go ahead and we look at this, I'll do this a little bit more quickly than we normally would, but notice that negative x6, notice as soon as I said we'll do it quickly, I make a mistake, that's karma. So negative x6 equals 0, that's x6 equals 0. Then negative x5 plus x6 is supposed to be 0. We just figured out x6 is 0, so that tells us that x5 is going to be 0. Then we would get that negative x4 plus x5 is supposed to be 0, because there's no x6 in this guy, but we just figured out that x5 is supposed to be 0, so x4 is going to be 0. Then we got negative 2x3 plus x4 plus 2x6 is 0. But that's nice and easy because x4 and x6 are both 0, so x3 must be 0. I think hopefully we can see the pattern here. And then finally, in the last equation, we have negative 2x2 plus, what is that, x4 plus x5 is equal to 0. But since everything else is already equivalent to 0 there, we know that x2 is also going to be equal to 0. So what this basically tells us, right, is that if we take a look at that, right, the eigenvectors, we can even phrase it as the eigenspace now. The eigenspace for lambda equals 2 is everything that is of the form t and then 0, 0, 0, 0, 0. Obviously, if you wanted a basis for the eigenspace, you would use something like 1, 0, 0, 0, 0, 0, right? 1 with all zeros, where you just do your standard way of finding a basis once you have the general eigenspace, or the general element. So the eigenspace for this is equal to this here. That also tells us that the dimension of E for lambda equals 2 is equal to 1, since we wanted to find all those dimensions. Okay, so there we go. This guy was pretty simple. We already knew that this was going to be the case. Next one that we want to do was we had lambda equals 0. So let's go ahead and do that. We'll give ourselves another page here. So now we're going to be doing lambda equals 0. Let's say what we're actually doing. Eigenvectors for lambda equals 0. So we'll subtract 0 off the diagonal and then go ahead and augment with the 0 vector and try to solve that. So looks like we get 2, 0, 1, 0, 0, 2. And then 0, 0, 0, 1, 1, 0. And then 0, 0, 0, 1, 0, 2. And then 0, 0, 0, 1, 1, 0. And then 0, 0, 0, 0, 1, 1. And then 0, 0, 0, 0, 0, 1. And then all zeros there. Okay, so a little bit messy to go ahead and directly solve this, but hopefully we can figure out how we would like to do this, right? If we take a look at this, it's actually already in pretty decent form. We could do a little bit of sort of clearing. We could use this guy to remove the stuff below that. So let's go ahead and just do a few operations here, right? But let's go ahead and do row 3 and replace it with row 3 minus row 2. And we'll do row 4 and replace it with row 4 minus row 2. So it looks like on top here we'd have 2, 0, 1, 0, 0, 2, and then 0. And then we'd have 0, 0, 0, 1, 1, 0, and 0. And then we have 0, 0, 0, and then 0. And then looks like minus 1 and 2 and 0. And then we'd also have 0, 0, 0, 0, 0, 0. So we get a 0 row there. And then also looks like we'd have 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 0, 0, 1, 0. Okay, so things are looking a little bit better. Now we're going to need to use this guy, it looks like, to clear out the stuff below there. So let's go ahead and do that. So it looks like we should be using row 5 and replacing with row 5 plus row 3. So if we do that, 2, 0, 1, 0, 0, 2. And then 0, 0, 0, 1, 1, 0, and 0. And then 0, 0, 0, 0 minus 1, 2, 0. And then on that 0 row, which we'll put at the bottom, and 0. And then 0, 0, 0, 0, we're adding that guy on, so 0, 3, and 0. And then 0, 0, 0, 0, 0, 1, 0. All right, last thing we can do is we can use, say, this guy to remove this. So we'll do a couple things sort of simultaneously. We'll go ahead and we'll do R6 and replace it with R6 minus 1/3 R5. And then we'll also, after we do that, interchange row 4 and row 5. And once we do that, we should have 2, 0, 1, 0, 0, 2, 0. And then 0, 0, 0, 1, 1, 0, 0. And then 0, 0, 0, 0, minus 1, 2, 0. And then 0, 0, 0, 0, 0, 3, because we're doing that interchange. And then we will have 2, 0 rows at the bottom here. Okay, so that does put us in row echelon form, because you can see there's our lead position, there's lead position, there's lead position, there's a lead position. So we're going to avoid parameterizing these guys. Notice that because we got 2 0 rows, it tells us that we're going to have a rank of 4. Since we have 6 variables, that means we're going to have 2 free parameters. So we're going to get a dimension of 2, which matches the multiplicity, which is a good sign for everything being non-defective overall. So let's go ahead and let's let x2, I guess we usually do it backwards. So let's let x3 be 2 and x2 be s. Those are the ones that we want to make sure that we actually parameterize. So we get 3x6 is supposed to be 0. So I guess x6 is supposed to be 0. We get negative x5 plus 2x6 is supposed to be 0. But that tells us that x5 is supposed to be 0. We get x4 plus x5 is supposed to be 0, which tells us x4 is supposed to be 0. But then, more interestingly, we get 2x1 plus x3. What is that? Plus x6 plus 2x6 is supposed to be 0. Now, if we think about that, that's going to give us that 2x1 plus t plus 0 is supposed to be 0. So it looks like x1 is supposed to be negative 1/2 t. So we can say that the eigenspace for lambda equals 0, which we would call E lambda equals 0, is everything that is going to look like negative 1/2 t, s, t, and then 0, 0, 0. So we got here that the dimension of E lambda equals 0 was equal to 2, right? Because we have two free parameters there. Again, a basis would be something like negative 1/2, 0, 1, 0, 0, 0, and 0, 1, 0, 0, 0, 0. Right, just changing, letting one parameter say t equal 1 and s equals 0, and then t equals 0, s equals 1 as normal. So notice that this was one of the two options that we sort of mentioned, right? We said that the dimension of this eigenvalue, since its multiplicity was 2, was either going to be 1 or 2, and in this case, it is equal to 2. So we've got one last one to do, which has the most sort of interest or most opportunities, which is the eigenvalue that had a multiplicity of 3, so the dimension of its eigenspace could be 1, 2, or 3. So let's go ahead and do that. That eigenvalue, if we go back and check, was lambda equals 1, so we'll investigate that guy. So let's give ourselves one more page here. So now eigenvectors for lambda equals 1. So we'll subtract 1 off the diagonal and then augment with the 0 vector. So 1, 0, 1, 0, 0, 2, 0, minus 1, 0, 1, 1, 0, 0, 0, minus 1, 1, 0, 2, then 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, and then 0, 0, 0, 0, 0, 0. And then augment with 0, 0, 0, 0, 0, 0. All right, we take a quick glance. There's a lead position, there's a lead position, there's a lead position, there's a lead position, and there's a lead position. This guy's actually already in row echelon form, so we'd want to avoid parameterizing here, 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 and here. Notice that this guy has rank 5, so we're only going to get one free variable from 6 minus 5. Right there, you guys should realize that the dimension of this eigenspace is only going to be equal to 1, and we're actually going to have a defective matrix here because this had multiplicity 3, and we're only going to get a one-dimensional eigenspace. Let's go ahead and take a look at what that would be. So we're going to let, what is that, x4 in this case be equal to t. We're going to get that x6 is supposed to be equal to 0. The next equation is going to tell us that x5 is supposed to be equal to 0. Then we're going to get that negative x3 plus x4 plus 2x6 is supposed to be 0. So negative x3 plus t is supposed to be 0. So x3 is supposed to be t as well. Then the next equation would tell us that x2 plus x4 plus x5 is supposed to be 0. But since we have x4 equal to t, so that's going to be x2 plus t plus 0 equals 0. So x2 is supposed to be negative t. And then finally, for the last guy there, looks like we would get the equation x1 plus x3 plus 2x6 is supposed to be equal to 0. But we already found that, we already found that x6 is supposed to be 0. So here it looks like we get x1 plus t equals 0. x1 equals negative t. So it looks like the eigenspace for lambda equals 1, which we could denote as E lambda 1, would be equal to anything that is of the form negative t, 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 0, 0. There we go. So that would be our eigenspace there. Now, since that only had a one free parameter, that would tell us that the dimension of that eigenspace, E lambda 1, is equal to 1. And if we check there, that is less than the multiplicity for lambda equals 1, which was equal to 3. And that would tell us that A is defective. In other words, another way of sort of phrasing that A is defective is that there is no way to construct a basis for R6 using just eigenvectors of A, right? Because if we go back through this, right, we found there's one thing, there's two more there, and there's a fourth one there. But unfortunately, we're missing two more linearly independent vectors. There's no two other eigenvectors here, unless we use linear combinations of the ones we already have, which we know won't be a basis. So this would be an example of a defective matrix. So the reason I wanted you guys to sort of see this example, even though it's a little bit lengthy in the computation, is just to show you guys some of the interesting things that can happen. Notice that here we did have a multiplicity greater than 1. We had a repeated eigenvalue, but its dimension actually matched that multiplicity. But here, well, unfortunately, the dimension was less than that multiplicity, which led to A being defective here. In our next video, we'll be starting to take the linear algebra concepts that we've talked about and begin applying them back to differential equations with Chapter 8.